Welcome to my second class on Kalman filters. I want to take you on a little tour to where it all began. Stanford University, behind me is Vail, Stanford's Automotive Research Center, and let's go inside. So this is Junior, Stanford's most recent self-driving car. It's the child of Stanley, whom you can find in the National Museum of American History in Washington, D.C. And let me tell you something about the equipment that's on this car that makes it self-driving. So this rotating thing over here is a laser rangefinder that takes distance scans 10 times a second, about 1 million data points. It'll be really important for the Kalman filter class that I'm teaching you today. Its major function is to spot other cars so you don't run into them. There's also a camera on top. There's a stereo camera system over here. And in the rear, there are antennas for a GPS, a global positioning system, that allows us to estimate where the car is in the world. This is a supplemental system to the localization class I just taught you. This is the data that comes from the laser. You can see the car parked in the garage right now. You see the back wall. These are all range measurements that tell you how far things are away, and they're essential as the input to the Kalman filter that we're going to learn about today.
Hi! I hope you're enjoying this free course. Sebastian's going to teach you about Kalman filters and how to use them, both to predict where you are in the world and where other vehicles are. Kalman filters are a key tool for self-driving cars. But, as you might imagine, the math gets much more complicated in the real world. The Self-Driving Car Engineer Nanodegree program takes what Sebastian teaches here and builds on it to show you how to work with radar and LiDAR data and how to program a Kalman filter for realistic, non-linear motion. These are the types of tools you'll need to work with if you want to join a self-driving car team. So join us in the Nanodegree program and become a self-driving car engineer with Udacity.
So I'd like to take my students onto a little journey to Stanford and show them our self-driving car that uses sensors to sense the environment. So let me dive into the class pretty much right now. So in our last class we talked about localization. We had a robot that lived in an environment and that could use its sensors to determine where in the environment it is. So here you can see the Google self-driving car using a road map localizing itself. But in addition, what's shown here in red are measurements of other vehicles. The car uses lasers and radars to track other vehicles. And today we're going to talk about how to find other cars. The reason why we'd like to find other cars is because we wouldn't want to run into them. So we have to understand how to interpret sensor data to make assessments, not just where these other cars are, as in the localization case, but also how fast they're moving. So we can drive in a way that avoids collisions with them in the future. That's important not just for cars, it matters for pedestrians and for bicyclists. And understanding where other cars are and making prediction where they're going to move is absolutely essential for safe driving in the Google Car project. So in this class we'll talk about tracking. And the technique I'd like to teach you is called a Kalman filter. This is an insanely popular technique for estimating the state of a system. It's actually very similar to the probabilistic localization method we talked in the previous class, Monte Carlo localization. The primary differences are that Kalman filters estimate a continuous state, whereas in Monte Carlo localization we are forced to chop the world into discrete places. And as a result, the Kalman filter happens to give us a unimodal distribution. And I'll tell you in a second what that means. Whereas Monte Carlo was fine with multimodal distributions. Both of these techniques are applicable to robot localization and tracking other vehicles. In fact, in the later class we're going to learn about particle filters, which are yet another way to address the same problem. And indeed they're actually continuous and multimodal. But for the time being, let's look into Kalman filters and ignore these other two families of methods. Let me start with an example. Consider the car down here. Let's assume it sees in this measurement an object here, 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 and here. With the times t equals 0, t equals 1, 2, and 3. Where would you assume the object would be at t equals 4? Check one of those three boxes. And yes, you'd expect it right over here. From those observations, you would say that the velocity points in the direction of this vector. So assuming no drastic change of velocity, you expect that the fifth position be over here. So the Kalman filter takes observations like these, estimates future locations and velocities based on data like this. And today I'm going to teach you how to write a piece of software that lets you take points like those, even if they're noisy and uncertain, and estimate automatically where future locations might be and at what velocity the object is moving. The Google self-driving car uses methods like these to understand where other traffic is based on radar and laser range data. So let's dive in. You remember our Markov model where the world was divided into discrete grids and we assigned to each grid cell a probability. Such a representation of probability over spaces is called a histogram, in that it divides the continuous space into finally many grid cells and approximates the posterior distribution by a histogram over the original distribution. And the histogram is a mere approximation to this continuous distribution. In Kalman filters, the distribution is given by what's called a Gaussian. Gaussian is a continuous function over the space of locations, and the area underneath sums up to 1. So here's our Gaussian again. And if we call the space x, then the Gaussian is characterized by two parameters. The mean, often abbreviated with the Greek letter mu, and the width of the Gaussian, often called the variance. And for reasons I don't want to go into, it's often written as a quadratic variable, sigma square. So any Gaussian in 1D, which means the parameter space over here is one-dimensional, is characterized by mu and sigma square. So rather than estimate the entire distribution as a histogram, our task in Kalman filters is to maintain a mu and a sigma square that is our best estimate of the location of the object we're trying to find. The exact formula is an exponential of a quadratic function, where we take the exponent of this complicated expression over here, the quadratic difference of our query point x relative to the mean mu, divided by sigma square, multiplied by minus a half. Now if x equals mu, then the enumerator becomes 0, and we have x of 0, which is 1. It turns out we have to normalize this by a constant, 1 over the square root of 2 pi sigma square. But for everything we talk about today, this constant won't matter, so ignore it. What matters is we have an exponential of a quadratic function over here. So let me draw you a couple of functions, and you tell me which one you believe are Gaussian by checking the box on the right side. And please excuse my poor drawing skills here. And the answer is this one is a Gaussian, this one, and this one. And they're all characterized by this exponential drop-off on both sides. They're symmetrical. And they have a single peak that's called unimodal. This is a bimodal function, has two peaks. And as a result, it's non-Gaussian. The same is true over here and over here. So these guys don't qualify. So let me ask you again about your intuition. And draw 3 more Gaussians. And again, excuse my poor drawing skills here. And now I'm going to ask you about the covariance. So for each of those, check exactly one box. Is the covariance large, medium, or small? Obviously, one of those is the largest, one is a medium, and one is small. And the answer is this is the largest covariance. It's the widest spread. This is the smallest, and this is medium. And to see how this is being found in the formula over here, the difference between x and y is being normalized by the covariance. So the larger this value, the less the difference over here matters. And as a result, the more the function is spread out. So functions with very wide spread have the largest covariance, whereas functions with small spread have the smallest covariance. Put differently, the sigma square covariance is a measure of uncertainty. The larger sigma square, the more uncertain we are about the actual state. This is a very certain distribution, where our expected deviation is small. This is a relatively uncertain distribution, where we know very little. So if we track another car with our Google self-driving car, which Gaussian would we prefer? The first, second, or third? And the answer is the third, because that's the one that's most certain. And because it's most certain, it makes the chance of accidentally hitting another car the smallest, just by the fact that we know more about the car than in the two other distributions. So you learned something really important. You learned the definition of a Gaussian. You learned about the fact that these are unimodal distributions. They're also symmetrical. And you learned a little bit about how to use them as a belief in a probabilistic filter. So let's go and program a Gaussian. So let me ask you to calculate the value of f of x. You will need a calculator for this. For the following values: mu equals 10, sigma square equals 4, x equals 8. And the approximate answer is 0.12. X minus mu square is 4, which is 10 minus 8 to the square, divided by 4 equals 1. So the expression in the exponential is minus a half, which is about 0.6. And this guy over here is approximately 0.2, which gives us as a product 0.12. So I won't torture you with any more questions like these because they're really not fun, but we can program this now. So starting with the following source code, I'm looking for a completion of this one line over here that returns the Gaussian function with arguments mu equals 10, sigma square equals 4, and x equals 8. And I want the output to be approximately 0.12. So here's my solution. This is the constant 1 over square root of 2 times pi times sigma. And then I multiply with the exponential of minus 0.5 times x minus mu square over sigma square. And that applied to the following numbers over here gives me 0.12. Now here's a question for you. How do I have to modify x, the 8, to get the maximum return value for this function f? And the answer is I set it to the same value as mu, in which case this expression over here becomes 0 and we get the maximum, we get the peak of the Gaussian. So we set x to the same value as mu, to 10, and the output is 0.2 approximately. So now let's look at the Kalman filter. The Kalman filter represents all distributions by Gaussians. And just like in the last class where we talked about measurement cycles and motion cycles, the Kalman filter iterates two different things: measurement updates and motion updates. So this is identical to the situation before in localization, where we got the measurement and then we took a motion. Here the math changes, but the basic principle applies. So let's do a quiz to see if you remember the material from last class. You might remember that one of the two steps, measurement or motion, required a convolution and the other one a product. Please check the corresponding box. Measurements were implemented using products and motion using a convolution. And if you don't know this, please go back and check the last class on localization. In fact, we talked about Bayes' rule and we talked about total probability. Please again check whether Bayes' rule and total probability apply to measurements or motions. And the answer is the measurement, the product, was using Bayes' rule, and motion was using total probability. So in Kalman filters, we iterate measurement and motion. This is often called a measurement update, and that's often called prediction. And the update will use Bayes' rule, which is nothing else but a product or a multiplication. And this update will use total probability, which is a convolution or simply an addition. Let's talk first about the measurement cycle and then the prediction cycle using our great Gaussians for implementing those steps. So suppose you're localizing another vehicle and you have a prior distribution that looks as follows. It's a very wide Gaussian with the mean over here. And now say we get a measurement that tells us something about the localization of the vehicle, and it comes in like this. It has a mean over here called nu, and this example has a much smaller covariance for the measurement. This is an example where in our prior we were fairly uncertain about a location, but the measurement told us quite a bit as to where the vehicle is. So here's a quiz for you. Will the new mean of the subsequent Gaussian be over here, over here, or over here? Check one of these three boxes. And the answer is over here in the middle. It's between the two old means, the mean of the prior and the mean of the measurement. And it's slightly further on the measurement side because the measurement was more certain as to where the vehicle is than the prior. The more certain we are, the more we pull the mean in the direction of the certain answer. Now here's a question that's really hard. When we graph the new Gaussian, I can graph one that's very wide, that's very peaky. So if I were to measure where the peak of the new Gaussian is, this would be a very narrow and skinny Gaussian. This would be one whose width is in between the two Gaussian. And this is one that's even wider than the two original Gaussians. Which one do you believe is the correct posterior after multiplying these two Gaussians? This is an insanely hard question. I'd like you to take your chances here and I'll explain you the answer in just a second. And very surprisingly, the resulting Gaussian is more certain than the two component Gaussians. That is, the covariance is smaller than either of the two covariances in the installation. And intuitively speaking, this is the case because we actually gain information. The two Gaussians together with higher information content than either Gaussian installation. So it looked like something like this. And that is completely non-obvious. And you might have to take this with faith. But I can actually prove it to you. Suppose we multiply two Gaussians as in base rule. A prior and a measurement probability. And the prior has a mean of mu and a variance of sigma square. And the measurement has a mean of nu and a covariance of r square. And the new mean, mu prime, is the weighted sum of the old means, where mu is weighted by r square, nu is weighted by sigma square, normalized by the sum of those weighting factors. And the new variance term, I'm going to write sigma square prime here for the new one after the update, is given by this equation over here. So let's put this into action. We have a weighted mean over here. Clearly, the prior Gaussian has a much higher uncertainty, therefore sigma square is larger. And that means the nu is weighted much larger than the mu. So the mean will be closer to the nu than the mu, which means it'll be somewhere over here. Interestingly enough, the variance term is unaffected by the actual means. It just uses the previous variances and comes up with a new one that's even peakier. So the result might look like this. So this is the common situation for the measurement update step, where this is the prior, this is the measurement probability, and this is the posterior. So let's practice these equations with a simple quiz. So here are our equations again. And suppose I use the following Gaussians. These are Gaussian with equal variance, but different means. They might look as follows. Compute for me the new mean after the update and the new sigma square. And the answer for the new mean is just the one in the middle, and the reason is both weights over here are equivalent. So we take the mean between mu and nu, which is 11. And the new sigma square is 2. If you take 1 over 4 plus 1 over 4, then we get 1 over 2. So 1 over 1 over 2 equals 2, which means the new variance term is half the size of the previous variance terms. Let's do this again. Suppose our mean is 10 and 13, and the variances are imbalanced, 8 and 2, which corresponds to the following picture. There's a relatively shallow distribution centered on 10, and a much more peaky distribution centered on 13. Compute for me what the resulting mu prime and sigma square prime are. And with a little bit of math, we find out that the new mean is 12.4, and the new sigma square is 1.6. 12.4 is much closer to 13 than 10, and that's because the Gaussian centered on 13 has a much narrower variance than the one on 10. And we find that the resulting variance is smaller than each of the two variances over here. In particular, let's start with the variance. 1 over 1 over 8 plus 1 over 2 is the same as 1 over 5/8, which results to 8/5, or 1.6. This is just applying this formula over here. For the weighted average, we get 2 times 10 plus 8 times 13, and then we normalize by the sum of those two things over here. So this is 124 divided by 10 gives us 12.4. Let me ask a different quiz, which follows from the math, but it tests your intuition. Suppose we have a prior that sits over here and a measurement probability that sits over here, really far away, and both have the same covariance. Let me first quiz you where the new mean would be. Is it going to be here, 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 or here? Please check the corresponding check mark. And the answer is here. It's in the middle. It's in the straight middle because these two variances are the same, so we just average the means. Let me ask the hard question now. Will it be a Gaussian like this, where the variance is larger, a Gaussian with the exact same variance, or an even more peaky Gaussian that's more certain than the two original factors in this calculation? Please check exactly one of the three boxes over here. And the answer is it's the more peaky Gaussian. That is somewhat counterintuitive. You'd think if this is your initial guess, this is your measurement probability, you really don't know where you are and you should pick a very wide Gaussian. But the truth is, our new sigma square is obtained independent of the means. It's this formula over here. Now, because both means are the same, this resolves to 1 over 2 over sigma square, and that's the same as sigma square over 2, which means the new variance square is half of the old one. That makes it a narrower Gaussian. So this one, the green one here, that's the most peaky, is indeed the correct answer. This is very counterintuitive, but now you understand why. And I hope you feel comfortable with the fact that we've actually gotten more information about the location, which is manifest by a more focused estimates. So let's now go back and write a program in which we calculate the new mean and the new variance term. So I really just want you to write a Python program that implements those equations so we can test them. I'm giving you a skeleton program which has a function update that takes as an input a mean and a variance for the first distribution and a mean and variance for the second distribution, and outputs the new mean and the new variance of the product of those. And here I'm testing it with a mean of 10 and a variance of 8 and a mean of 13 and a variance of 2, which was one of our examples. And out should come the answer over here, 12.4 and 1.6. Of course, Python tends to not give you the exact output, so there's a couple of zeros over here, but ignore those. The answer is effectively 12.4 and 1.6. Can you fill in those gaps? And here's my answer. This is the expression for the mean. This is the one for the variance. I run it. I get the exact same answer. I run it again for my other example of equal variances and 10 and 12 as a mean. And miraculously, the correct answer comes out. 11 for the new mean and 2 for the new variance square. If you program this correctly, then congratulations, you've just programmed an essential update step in the Kalman filter, the measurement update step. That's really the difficult step in Kalman filtering. The other one, the prediction step or the motion step, is much, much easier to program. So let's step a step back and look at what we've achieved. We knew there was a measurement update and a motion update, which is also called prediction. And we know that the measurement update is implemented by multiplication, which is the same as base rule. And the motion update is done by total probability, or an addition. So we tackled the more complicated case. This is actually the hard one mathematically. And we solved it. We gave an exact expression. We even derived it mathematically. And you were able to write a computer program that implements this step of the Kalman filter. I don't want to go into too much depth here. This is a really, really easy step. Let me write it down for you. Suppose you live in a world like this. This is your current best estimate where you are, and this is your uncertainty. And now say you move to the right side a certain distance, and that motion itself has its own set of uncertainty. Then you arrive at a prediction that adds the motion command to the mean, and it has an increased uncertainty over the initial uncertainty. And intuitively this makes sense. If you move to the right by this distance, in expectation you are exactly where you wish to be, but you've lost information because your motion tends to lose information as manifest by this uncertainty over here. Now the math for this is really, really easy. Your new mean is your old mean plus the motion, often called u. So if you move over 10 meters, this would be 10 meters. And your new sigma square is your old sigma square plus variance of the motion Gaussian. This is all you need to know. It's just an addition. And I won't prove it to you because it's really trivial. But in summary, we have a Gaussian over here. We have a Gaussian for the motion with u as the mean and r square as its own motion uncertainty. And the resulting Gaussian in the prediction step just adds these two things up. Mu plus u and sigma square plus r square. Since it was so simple, let me quiz you. We have a Gaussian before the prediction step, for which mu equals 8 and sigma square equals 4. We then move to the right, a total of 10, with a motion uncertainty of 6. Now describe to me the predicted Gaussian and give me the new mu and the new sigma square. And the answer is just add those up. 8 plus 10 equals 18. 4 plus 6 equals 10. And that's it. So let's program this. I'm giving you a skeleton code. This is the same update function as before. And now I would like you to do the predict function, which takes our current estimate and its variance and the motion and its uncertainty and computes the new updated prediction, mean, and variance. So for example, if our prior is 10 and 4, our motion is 12 and 4, I would like to get out 22 and 8 according to the formulas I just given you. And yes, it's as easy as this. We just add the two means and the two variances. It's amazing. This entire program over here implements a one-dimensional Kalman filter. So now let's put everything together. Let's write a main program that takes these two functions, update and predict, and feeds it into a sequence of measurements and motions. The example I've chosen here is the measurements are 5, 6, 7, 9, and 10. The motions are 1, 1, 2, 1, 1. This all would work out really well if the initial estimate was 5, but we're setting it to 0 with a very large uncertainty of 10,000. Let's assume the measurement uncertainty is constant 4 and the motion uncertainty is constant 2. And when you run this, your first estimate for position should basically become 5, 4.99. And the reason is your initial uncertainty is so large, the estimate is dominated by your first measurement. Your uncertainty shrinks to 3.99, which is slightly better than the measurement uncertainty. You then predict that you add 1, but the uncertainty increases to 5.99, which is the motion uncertainty of 2. You update again based on the measurement 6. you get your estimate of 5.99, which is almost 6. You move 1 again, you measure 7, you move 2, you measure 9, you move 1, you measure 10, and you move a final 1. And out comes, as the final result, a prediction of 10.99 for the position, which is your 10 position moved by 1, and the residual uncertainty of 4. Can you implement this so you get exactly the same outputs as I've gotten over here? So this piece of code implements the entire Kalman filter. It goes through all the measurement elements, and it quietly assumes there's as many measurements as motions, indexed by n. It updates the mu and sigma using this recursive formula over here, where we plug in the nth measurement and the measurement uncertainty. It does the same with the motion, the prediction part over here. It updates the mu and sigma recursively using the nth motion and the motion uncertainty, and it prints all of those out. So if I hit the run button, I find that my first measurement update gets me effectively 5.0. It's 4.98. And that makes sense because we had a huge initial uncertainty and we just observed 5 with a relatively small measurement uncertainty. In effect, the resulting sigma squared term is 3.98, which is better than 4 and 1,000, slightly better than 4. So we're slightly more certain than the measurement itself. We now apply the motion of 1. We get to 5.9. Our uncertainty increases by exactly 2, from 3.9 to 5.98. And then the next update comes in at 6. And that gives us a measurement of 5.99. And now a reduced uncertainty of 2.39. And then we're going to move to the right again by 1, which makes the prediction 6.99. Uncertainty goes up. We measure 7. We get to 6.99, almost 7. Uncertainty goes down. We move 2 to the right, measure 9. 1 to the right, measure 10. And move 1 again. The final thing is in motion. And if you look at the end result, our estimate is almost exactly 11, which is the result of 10 plus 1. And the uncertainty is 4.0 after the motion and 2.0 after the measurement. This code that you just wrote implements a full Kalman filter for 1D. So if you look at this, we have an update function that implements what actually is a relatively simple equation, and a prediction function which has an even simpler equation of just addition. And then we apply it to a measurement sequence and a motion sequence with certain uncertainties associated. And this little piece of code over here gives you a full Kalman filter in 1D. I find this really amazing. So let's plug in some other values. Suppose you're really certain about the initial position. It's wrong, it's 0. It should be 5, but it's 0. And now we assume a really small uncertainty. Guess what's going to happen to the final prediction? As I hit the run button, we find this has an effect on the final estimate. It's not 11, it's only 10.5. And the way this takes place is, initially, after our first measurement update, we leave in the position of 0. This is 1.24 to the minus 10th, with a really small uncertainty, even smaller than this one over here. We apply our motion update, we add a 1, we have a higher uncertainty. And now when the next measurement comes in 6, we are now more inclined to believe the measurement because our uncertainty is now basically 2 as opposed to 0.001. So we update our position to be 2.666, which is now a jump away from 1, and we reduce our uncertainty. Motion comes in 3.66, uncertainty goes up. We're now willing to update even more. As we see the 7, we're willing to go to 5.1, but not quite all the way because we feel fairly confident in our wrong prior estimate. And this confidence makes it all the way to the end, when we predict 10.5 as opposed to 11, with a residual uncertainty of 3.98. So we've corrected some of it. We were able to drag it into the right direction, but not all the way, because our false initial belief has such a strong weight in the overall equation. So now we understand a lot about the 1D Kalman filter. You've programmed one. You understand how to incorporate measurements. You understand how to incorporate motion. And you really implement something that's actually really cool, which is a full Kalman filter for the 1D case. Now in reality, we often have many Ds. And then things become more involved. So I'm going to just tell you how things work with an example and why it's great to estimate in higher dimensional state spaces. Suppose you have a two-dimensional state space of X and Y, like a camera image. Or in our case, we might have a car that uses a radar to detect the location of a vehicle over time, then what the 2D Kalman filter affords you is something really amazing. And here's how it goes. Suppose at time t equals 0, you observe the object of interest to be at this coordinate. This might be another car in traffic for the Google self-driving car. One time step later, you see it over here. Another time step later, you see it right over here. Where would you now expect at time t equals 3 the object to be? Let me give you 3 different places. Please click at the most likely location. And the answer is here. What the Kalman filter does for you if you do estimation in higher dimensional spaces is to not just go into x and y spaces, but allows you to implicitly figure out what the velocity of the object is, and then use this velocity estimate to make a really good prediction about the future. Now notice, the sensor itself only sees position. It never sees the actual velocity. The velocity is inferred from seeing multiple positions. So one of the most amazing things about Kalman filters in tracking applications is that it's able to figure out, even though it never directly measures it, the velocity of the object, and from there is able to make predictions about future locations that incorporate velocity. That is just really, really, really great. And that's one of the reasons why Kalman filters are such a popular algorithm in artificial intelligence and in control theory at large. To explain how this works, I have to talk about high-dimensional Gaussians. These are often called multivariate Gaussians. The mean is now a vector with one element for each of the dimensions. The variance square is replaced by what's called a covariance, and it's a matrix with d rows and d columns if the dimensionality of the estimate is d. And the formula is something you have to get used to. I'm writing it out for you, but you'll never get to see this again. Tell you the truth, even I have to look up the formula for this class, so I don't have it in my head. And please don't get confused. Let me explain it to you more intuitively. Here's a two-dimensional space. A two-dimensional Gaussian is defined over that space, and it's possible to draw the contour lines of the Gaussian. They might look like this. The mean of this Gaussian is this x0, y0 pair. And the covariance now defines the spread of the Gaussian as indicated by these contour lines. A Gaussian with small amounts of uncertainty might look like this. It might be possible to have a fairly small uncertainty in one dimension, but a huge uncertainty in the other. Here the uncertainty in the x dimension is small, in the y dimension is large. And when the Gaussian is tilted, as shown over here, then the uncertainty of x and y is correlated, which means if I get information about x that actually sits over here, that would make me believe that y probably sits somewhere over here. That's called correlation. I can explain to you the entire effect of estimating velocity and using it in filtering using Gaussians like these, and it becomes really simple. The problem I'm going to choose is a one-dimensional motion example. Let's assume at t equals 1, we see our object over here. At t equals 2, right over here. At t equals 3 over here. Then you would assume that at t equals 4, the object sits over here. And the reason why you would assume this is, even though we've just seen these different discrete locations, you can infer from it there is actually velocity that drives the object to the right side, to the point over here. Now, how does a Kalman filter address this? This is the true beauty of the Kalman filter. In Kalman filter land, we're going to build a two-dimensional estimate, one for the location and one for the velocity, denoted x dot. Where the velocity can be 0, it can be negative, or it can be positive. If initially I know my location but not my velocity, then I represent it with a Gaussian that's elongated around the correct location, but really, really broad in the space of velocities. Now let's look at the prediction step. In the prediction step, I don't know my velocity, So I can't possibly predict what location I'm going to assume. But miraculously, there is some interesting correlation. So let's for a second just pick a point on this distribution over here. Let me assume my velocity is 0. Of course, in practice, I don't know the velocity, but let me assume for a moment the velocity is 0. Where would my posterior be after the prediction? Well, we know we start at location 1 with velocity of 0, so my location would likely be here. Now let's change my belief of the velocity and pick a different one. Let's say the velocity is 1. Where would my prediction be one time step later, starting at location 1 and velocity 1? I give you 3 choices. Here, here, or here. Please pick the one that makes most sense. And the answer is right over here. Why? If our current starting point is the point over here, for which we know the location is 1 and the velocity is 1, and if we predict one time step in the future, then for that prediction, we know the location will be 2, and the velocity might be a little bit uncertain, but it stays about the same. So we end up with a point over here. Let's do this again. Let me consider a velocity of 2, which means this is our starting point. And let me ask you where you would expect among those choices to be the most plausible prediction to be. And just like before, it'll be over here. With a velocity of 2, initial position of 1, we find ourselves in 3. And again, this model assumes that in the absence of more knowledge, the velocity shouldn't really change. When you put all this together, you find that all these possibilities on the Gaussian over here link to a Gaussian that lies like this. And this is a really interesting two-dimensional Gaussian, which you should really think about. Clearly, if you were to project this Gaussian uncertainty into the space of possible locations, I can't predict a thing. It's impossible to predict where the object is, and the reason is I don't know the velocity. Also, clearly, if I project this Gaussian into the space of x dot, then it's impossible to say what the velocity is. A single observation or a single prediction is insufficient to make that observation. However, what we know is our location is correlated to the velocity. The faster I move, the further on the right is the location. And this Gaussian expresses this. If I, for example, figured out that my velocity was 2, then I was able, under this Gaussian, to really nail that my location is 3. That is really remarkable. You still haven't figured out where you are. We haven't figured out how fast we're moving, but we've learned so much about the relation of these two things with this tilted Gaussian. And to understand how powerful this is, let's now fold in the second observation at time t equals 2. This observation tells us nothing about the velocity and only something about the location. So if I were to draw this as a Gaussian, it's a Gaussian just like this, which tells me something about the location, but not about the velocity. But if I now multiply my prior from the prediction step with the measurement probability, then miraculously I get a Gaussian that sits right over here. And this Gaussian now has a really good estimate what my velocity is and a really good estimate where I am. If I take this Gaussian and predict one step forward, then I find myself right over here. That's exactly the effect we have over here. As I update this, I get a Gaussian like this. I predict right over here. Think about this. This is a really deep insight in how Kalman filters work. In particular, we've only been able to observe one variable. We've been able, through multiple observation, to infer this other variable. And the way we've been able to infer it is that there's a set of physical equations which say that my location after a time step is my old location plus my velocity. And this set of equation has been able to propagate constraints from subsequent measurements back to this unobservable variable velocity, so we're able to estimate the velocity as well. This is really key to understanding Kalman filter. It is key to understand how a Google self-driving car estimates the location of other cars and is able to make predictions even if it's unable to measure velocity directly. So there's a big lesson here. The variables of a Kalman filter, they're often called states because they reflect states of the physical world, like where is the other car and how fast it's moving. They separate into two subsets: the observables, like the momentary location, and the hidden, which in our example is the velocity, which I can never directly observe. But because those two things interact, subsequent observations of the observable variables give us information about these hidden variables, so we can also estimate what these hidden variables are. So from multiple observations of the places of the object, the location, we can estimate how fast it's moving. That is actually true for all the different filters, but because Kalman filters happen to be very efficient to calculate, when you have a problem like this, you tend to often use just the Kalman filter. So when you design a Kalman filter, you need effectively two things. For the state, you need a state transition function, and that's usually a matrix. So we are now in the world of linear algebra. And for the measurements, you need a measurement function. So let me give you those for our example of the 1D motion of an object. We know that the new location is the old location plus velocity. Turn this into this matrix, you have a 1 over here and a 1 over here. The new velocity should just be the old velocity, because it's a 0 over here and a 1 over here. If you multiply this matrix with this vector, this is exactly what you're getting. And for the measurement, we only observe the first component, the place, not the velocity. And that uses a vector or a matrix like this. So this matrix will be called F, and this H. The actual update equations for a Kalman filter are involved. And I give them to you, but please don't memorize them, and I won't prove them for you. Even the proof is very involved. Every time I use them, I just look them up. There's a prediction step where I take my best estimate x, multiplied with the state transition matrix F, and I add whatever motion I know, u. That gives me my new x. I also have a covariance that characterizes my uncertainty, and that is updated as follows, where t is the transpose. There's also a measurement update step, where we use the measurement z. We compare the measurement with our prediction, where h is the measurement function that maps the state to measurements. We call this the error. The error is mapped into a matrix S, which is obtained by projecting the system uncertainty into the measurement space using the measurement function projection, plus a matrix R that characterizes the measurement noise. This is then mapped into a variable called K, which is often called the Kalman gain, where we invert the matrix S. And then finally, we actually update our estimate and our uncertainty using what ought to be the most cryptic equation that you've seen in a long time. Now, I wrote this down so that you have a complete definition, but this is something you should not memorize. If you really wish to understand this math, it happens to be just a generalization of the math I gave you to higher dimensional spaces. But I would recommend just not to worry about this. There is a set of linear algebra equations that implement the Kalman filter in higher dimensions. So I have a challenging programming assignment for you that'll kind of take you a while, but I would like you to implement a multidimensional Kalman filter for the example I've just given you. The matrix class is a class for manipulating matrices that should make it really easy. It has a function that initializes matrices. I'll show you an example in a second. It can set them down to 0. It can compute an identity matrix. It can print out a matrix with show. And it overloads operators like addition, subtraction, multiplication, and even computes the transpose of a matrix. And in some more extended code, it can actually invert a matrix using Cholesky factorization. So there's a function here called inverse. So this matrix class is available. It's a small version of what is found in typical libraries. And I want to demonstrate it for you just for a second. You can make a matrix with a command like this, where the argument in the parentheses is a two-dimensional matrix. In this case, it's a vertical vector. And with the show command, you can print out the result, a vertical vector. You can compute the transpose as follows. If you run this, you find a horizontal vector. And say you wish to multiply a matrix by a vector, then we can make a 2 by 2 matrix with this initialization over here, matrix of 12, 8 and 6, 2. We can print this matrix. Here it is, 12, 8, 6, 2. These are these values over here. And we can multiply f and a. So here b equals f times a. And if we show the result, we get the vector 280. That's obtained by 10 times 12 plus 10 times 8 is 200, 10 times 6 plus 10 times 2 is 80. So using my matrix libraries, I set an initial state. This is a tracking in 1D where the state is the position and the velocity. I initialize both with 0 because I don't know the actual location and the velocity. I give an uncertainty matrix where I have a really high uncertainty in the position and a really high uncertainty in the velocity, and they're both uncorrelated. That's the matrix of 1000, 0, 0, 1000. I specify an external motion, but it's 0, 0, so it has no effect, so just ignore this. I build a next state function, which is the one we just discussed, 1, 1, 0, 1. That assumes that the velocity is just being added to the position, and the velocity in expectation stays the same. I build a measurement function that extracts just the first of the two values, 1 and 0, so I can observe the location but not the velocity. I have a measurement uncertainty, happens to be 1 in this example, and I have an identity matrix, 1, 0, 0, 1. And then I run a filter with these three measurements over here. And what should come out is that by running the filter, I can estimate the velocity and therefore make better predictions. In the filter that I want you to program, I want the measurement update first and then the motion update. So every time we run the filter, I want you to update the measurement first, then the motion. So here's my empty procedure filter that you have to fill in, where I go through all measurements and then build the measurement update and then the motion update, the prediction, and then I just print out the resulting estimates. I do this a number of times, 3 times in this case. And once you fill this in and I hit the run button, I get the following output. After my first measurement update, I observed the location 1, which gets copied over essentially to 0.999 over here, and learned nothing about the velocity. So it's still 0, just the way I initialized it. And then there's an updated uncertainty matrix, which now shows what happens to be a strong correlation. 1000, 1000, 1000, 1000. That differs from the initial one, only that we filled in the off-diagonal elements. Happens to be exactly what the Kalman filter does. And then when I observe again the 2, I want the output to now tell me that my next prediction is 3. It's the observation plus the prediction. But now I have a really good estimate on what the velocity is. It's essentially 1. And the reason is my Kalman filter was able to use the Kalman filter equations to find this value. There's a new covariance matrix. And for the third observation, followed by the prediction is correctly, effectively 4, 3.999. Velocity estimate is correctly 1, which is 0.99999. And I have yet another uncertainty matrix, which illustrates I have high certainty in the velocity estimate and also relatively high certainty in the position estimate compared to my initial uncertainties. So can you write the algorithm filter that outputs those exact values over here? This is an involved programming assignment. What you have to do is you have to essentially implement the equations I gave you. You have to familiarize yourself with the matrix class and then go and fill in the filter code in accordance to the things that I showed you for the multivariate Kalman filter. And here's my code. If you got this correct, then I'm mightily impressed with what you've done, because You've taken something that often takes many classes to explain to students, and within a single class you understood the gist of it, and you wrote a piece of code that is really non-trivial, that you can reuse many times, and that's the core of the Google self-driving car's ability to track other vehicles. Here is the line-by-line implementation of what I've shown you before for the measurement update and the prediction. And you'll find, using my matrix class, that it implements step after step exactly what I've shown you. A little non-triviality: we have to make a measurement matrix or the nth measurement. If we solve the problem, we have probably something like this. The error calculation, the matrix S with the transpose, the Kalman gain K with the inverse, back to my next prediction and my measurement update. And this is the prediction step. You can see it implements exactly what I showed you in these two equations over here. Now, I know programming with this is involved, and I'm really impressed if you're able to do this. If you've done this, you would see something really major. You now understand Kalman filters, and you've implemented a multi-dimensional Kalman filter all on your own using a fairly mechanical matrix class that I wrote for you. You run it, and you've gotten a really good results in which a sequence of position estimates, 1, 2, 3, led you to make a prediction and understand the velocity of the moving object. So these are the equations you just implemented. Congratulations, you really understood something fundamental here that I believe is really essential to artificial intelligence and to building self-driving cars. You implemented effectively our method for finding other cars. Let me put this in context. Here's our Google self-driving car. Here's another car. Our Google self-driving car uses radar in the front bumper that measures the distance to vehicles and also gives a noisy estimate of the velocity. And it also uses its lasers. And again, it measures the distance to other cars, but no velocities. If we paint the same situation from above, here's the Google car. It is localized in a map. Here's another vehicle and another one, using radars and lasers. The Google car estimates the distance and the velocity of all these vehicles. And it does so using a Kalman filter, where it feeds in range data from the laser and uses state spaces like this one of the relative distance in x and y and the relative velocity in x and y, together with straight transition matrices of the type I've just shown you, to find out where these other cars are. And this is exactly what you've just learned and programmed yourself. I didn't tell you how to extract the location of other cars from radar and laser. There's something called a correspondence problem. Sometimes you don't know which one each car is, and I won't talk in much depth about it. But you understand the gist of the solution now, and you've been able to program it. So if you're in a situation like this, you can use range data, like laser data and radar data, and come up with a rational algorithm that takes momentary measurements of other cars, and not just estimates where they are, but also how fast they're moving. That's really a tremendous feat. Congratulations to getting this far. If you got this far in my class, I promise you, you've just digested the most difficult thing I have to teach you in this entire class. Congratulations. So this completes my unit on Kalman filters. You learned actually quite a bit. You learned about Gaussians, how to do measurement updates using multiplication, how to do prediction or state transitions using convolution. And you even implemented your first Kalman filter, which is really super cool. You've implemented in the context of vehicle tracking, and you used it to estimate a non-observable velocity from measurement data. Now, next is your homework assignment. I hope you can prove what you've learned and ace it. And then next week, we're going to move into particle filters, which is an exciting third method for state estimation. So I see you for the homework assignment, and then I'll see you in class for particle filters.